Alright, let's do another one. Today we're going to be working on number 268, missing number. Given an array nums containing n distinct numbers in the range 0 to n, return the only number in the range that is missing from the array. Okay. So there are a couple of brute force solutions that you can employ. You can, well, actually that might actually be the solution. We'll talk about that one later. Okay. First of all, the simple solution would be use a set, collect the numbers in nums, then check which number is missing. So this would be like for each number in nums, add to a set. For each number in the set, check. Oh, that would be a good question as to how you would do that. The brute force solution, I guess you could say, is add to a set and keep track of a maximum. And then for each number in 0 to the max, check if it exists within the set, right? So this would be O of n, because we'd just be adding it to a set, iterating through the numbers in the array. Pretty standard stuff. For each number in 0 to the max, check to see if it exists within the set. This would, again, be O of... Oh, that's a good question. Considering that it ranges from 0 to n, and there's one missing, that means the range is going to be, or the size of the array is going to be n plus 1 minus 1, so just n, I think. Could be wrong on that. But in any case, it's fairly linear, or fairly close to linear, I would say, because we're just iterating from 0 to the max. And that is technically while the maximum number can be very high, the maximum number being very high also means that because of the constraint of this problem, that the array itself will also accommodate that size. It will grow to be that size. So in a sense, the maximum number is essentially the size of the array. So both of them are bounded, we can say, by a singular n, where n can either represent the maximum number in the array or the size of the array. It doesn't matter because they're linked to each other. So the runtime here would be O of n, or linear time. And the space complexity in this case would also be O of n, because we would have to store one copy of every number except for the missing number. So same thing. It would be the same size as the array effectively. The other solution that I was thinking about that I initially said is a brute force solution, but might turn out to be the correct one, or a correct solution, we'll say, is to start by sorting using Radix sort, our good friend Radix sort, which is close enough to linear, then using a sliding window. So the idea is this: sort the array by number order, so least to greatest, as it were. Then, using a sliding window of size 2, check to see if the number on the left is one, or if number, the difference between the left and right numbers is 1. There's a corner case here for the first, in the case that we have something like, and I'll write this out. So if the number that is missing is the first number, that's 1. So 1, 2, 3, for example, right? Where the missing number, oh, actually in that case, no. It is not possible. It is not possible for the first number because the constraint of the problem dictates a range from 0 to n. So if n is 0, then of course we can't have that. So in this case, the smallest possible number that can be missing is 2. Because in this case, if we have n equals to 1, then there should be one number in the array. However, that is not the case because we always start with 0. So there must be one element. And therefore, the smallest number, missing number, is 2. However, there is a corner case 2 that actually does make sense, and that is within example 2 right here. And that is if the number at the end is not equal to nums.size minus 1, then the last number is missing. So in this case, the last number should be equal to, actually it's just nums.size. Right, so it's 0, 1. We set our sliding window here. This is fine because the difference of 1. However, the last number in this case is 1, where we want our number at the end to be equal to num's size, which is 2. Therefore, the missing number is 2. So, this, in this case, using a sliding window and using the sort, our runtime is effectively linear using Radix sort. Again, we are using numbers, so Radix sort should be valid. This is one way to accomplish the linear time runtime that is in the follow-up. It's hidden under here, but you can see the linear runtime complexity. It also says constant space. So the Radix sort allows us to run a sort in linear time, or close enough to linear time. And the sliding window approach means that we will have to iterate through each element effectively in our array with the sliding window of size 2. So that is also a linear, just scan through our array, and we're fine there. As for our space, this example does not hold any additional data, beyond what is given to us from the numbers array, because all we have to really check are our local numbers within our sliding window. So that's constant space. And I'm fairly confident in this solution. So let's give it a shot. Let's go ahead and start coding. So we'll run a sort, and I've already forgotten the sort. Looks like we should be able to just sort. And this should be an in-place sort. Then we will say var left window 0, window is equal to 1, n can be containing n distinct numbers in the range I'm curious as to n being equal to 1. If n is equal to 1, that means the length of the array is equal to 1. Then nums 0 equal to 1 return 0 because that's the missing one. Otherwise, return 1. In that case, yeah, the minimum smallest missing number is technically 1 because we could be missing 0 or 1 in that case. So this is actually a strange corner case. Do we need to account for this later on? Yes, because it is still possible for 0 to be missing from the array. And in that case, our first numbers will be 1 and 2. So if left window nums at left window is not equal to 0, then we return 0. This is corner case 1. In the case that we are missing 0. Check that the first number is always 0. Then we can say for I in 0 to nums length minus 1. We'll say minus 2, right? We can say val left is equal to I. Val right is equal to I plus 1. Because then the maximum number will be nums.length. Actually, this should be size minus 2 plus 1, so the last number, so minus 1. If nums at right minus nums at left is not 1, we want to return, what do we want to return in that case? In the case of something like a 0, 1, 3, we want to add them and divide by 2. But this is an even number. What happens if we are missing an odd number? In this case, 2 plus 4 is 6, divided by 3, or 2 is 3. It should be possible then to just return nums.right plus nums.left divided by 2. This could be incorrect. We'll see. Then, if all else fails, that means that that the first number is fine, that all the numbers leading up to the last number are fine, then we should return the size of the array, because that means that the last number then is the one that did not show up. So we start by checking to see if the size is 1, because then we don't want to run a sliding window for this, because it makes no sense, right? We want arrays of at least size 2. We then sort. So we start by sorting into increasing order. Then, if the first value is not 0, then we return 0, because that's the one that's obviously missing. Then we initialize our sliding window. We start with a left at our current pointer, our right at the next value, going all the way up until we've scanned all of them essentially on the right and left. And we check to make sure that each number compared to each other has a difference of 1. If it does not have a difference of 1, that means that there is a number between them which is missing. So, let's give this a run, and let's see if we need to change anything. Right, left window in this case is not established at that point now, because I've changed it to be inside. So that seemed to have worked. Let's run the rest of the test cases just to make sure that everything does work, and that we did not miss any other corner cases, at least within the examples, right? Everything looks fine so far. So let's give it a run, and let's see where we end up. Maybe there is a linear runtime solution with constant space that does not involve using a radix sort. And I could be completely wrong for this. And maybe this int array doesn't, this sort doesn't use radix sort, though I would be very surprised if it didn't, because radix sort is a very, very nice function. It's a very nice sorting algorithm for numbers. So, let's give it a submit, and let's see where we end up in time and space. Okay, so this is very, very slow, which seems to indicate that something here is not correct. In this case, it is probably that this sorting is slow, which is disappointing. So let me think about maybe another solution that maybe doesn't use linear, or that doesn't use radix sort, and maybe there's a way to achieve a better runtime than this. It might take me a bit, so I'm gonna go take a quick break, and I'll get back to you when I've either given up or when I've thought of maybe an approach that we can consider. Okay, I'm not sure this will end up making it in the video, but a couple of things here. One, the Kotlin sort relies on the Java sort. Makes sense. The Java sort is not radix sort, even for arrays of an integer value. It uses a sort of modified quicksort which seeks to maintain the quickness of it, but that quickness is still O of nlogn. That's not what we want. Second thing is that I just had a random thought that because the first thing is like, I'm not going to be implementing radix sort by myself, at least in this case. And I don't think that a LeetCode easy expects you to implement a radix sort. So in this case, I was thinking, what could I do to not sort? And one potential theory that popped into my head is there a way to accomplish our task using math? And there might be a way. The random thought in my head was, could we use summation? And this is usually kind of not really possible given the number of ways that we can achieve the summation of a number. However, in this case, we know that there is only one number that is missing, and I think that's our key to solving this problem. So, what I'm imagining is a potential mathematical solution. My theory is that if we add up all of the numbers and gather the maximum, we can get two values. The first value is the sum of our numbers. Pretty standard. And we don't actually need to gather the maximum, all we need is to gather the size. And get the size. We have two values, the sum of the numbers within our array, as well as the potential maximum if all elements within the array are present. And what made me think of this was actually the weird rabbit hole that we went down in a previous episode of another LeetCode easy problem, where we were thinking about the runtime of an algorithm if we had 1 plus 2 plus 3 plus 4 and on and on and on and on until n, right? And that formula is just n times n plus 1 divided by 2, I believe. So we have an explicit formula for what we need, or what we should get, and we have the sum of what we currently have. And because there is only one element that is missing within our array, then there is only one possible value which it could be. This is, I think, a very similar question in scope to something like twosum, in which because you only have two numbers that you care about, there is only one other possibility in which to create that number. We have a target number and we have what we have currently. Therefore, there can only be one complement number that we need to worry about. And I think that this problem might have something similar. So, our pseudocode would be something like the following. For each number in nums, add it up. Calculate the potential maximum using our num size and return the difference. And the beauty of this solution is that it works no matter what, no matter the size of our array. If the size is 0, if we had 0 or 1, in this case we know that 1 minus 0 is equal to 1, or 1 minus 1 is equal to 0. In whichever case, size is 1, obviously. In either case, we automatically sort of cover this corner case at the top. And we also cover this corner case at the bottom because of the fact that we have a potential maximum. So I think that's kind of... Is it weird to say that this solution is kind of beautiful in the sense that it covers both of those corner solutions without writing or carving out special cases for them? Var potential maximum equal to, and I believe that there's a cool method that we could use here. Is it fold? Take a look at the collections. Is it fold? Yes. Folds accumulates a value with an initial value. Okay. Awesome. So we can say that our value is nums.fold, where our initial value is 0. And we have an operation which is a lambda with our new value as well as our and applying the operation at each element. And this is an accumulator of type result and of type t. So this is our current. And the second one is our type, which will be, I believe, our new value, right? It seems to be, that's how it goes. And then this is what hopefully is actually returned. So we could potentially one-line this. And there might be an even more succinct way to sort of write this up. But this is how I think it works. And this is not our potential maximum, but rather our current maximum. Or, okay, we'll say current sum. And we'll let our potential sum is equal to nums.size times nums.size plus 1, wrap this up, divided by 2. And then all we need to do is return our potential sum minus current sum. So this basically just starts at 0. We get our current value, our new value, and then we return our current plus new into this accumulator. Our potential sum is just the harmonic series explicit formula to get that. I believe it's n times n plus 1 over 2. Could be wrong, might need to double check. And then we just return the result. So this is going to be O of n runtime, because we are just iterating through and calculating the sum. And of course, our space is going to be constant because we're just storing these two values without ever having to, where these values do not scale with regards to the size of the array. We are only storing these two integers no matter how many integers we have. So this is the proper O of n runtime, O of 1 space solution for this, I think. And it seems like our initial example test cases worked out. Let's see if we can improve on this runtime and memory. Okay, now that is a runtime and a space percentage that I like to see. That is beautiful. I think that's one of the highest that we've actually seen so far. So 98.40% runtime and 93.46% space. It took us a while to get here. However, we got there in the end. And I'm pretty happy about this. So I'm not sure what the lesson here is. I think that if we're dealing with arrays, particularly with integers, there's a potential way to math our way into a solution. However, there is, of course, always an algorithmic solution for those who are less mathematically inclined, such as myself, which is why it took so long to discover this. But I'm happy about it, and I hope you learned something. So with that, I'll see you for the next problem.